So today we're going to talk about different types of loadings and how that affects what profiles you're going to select. What I have here are two different profiles. This is our 50 millimeter heavy duty style profile, and this is our 40 by 80 lightweight profile. Let's talk about the different types of loadings. When you do T-slot aluminum framing, your structure is going to be loaded usually in one of two ways. You're going to have what's called an axial load, that is, say we're going to press down on this, or we're going to try and pull it apart. So we put the member in compression or in tension. The second way that we could load this is we could have it like a beam, where this is cantilevered like this, and I'm pushing down on this like this, and I'm trying to bend that. And the third way that you could load these is you could actually have like a twisting motion. It would be like a torque going down the axis of this. We recommend that you do not subject your structural framing to torsional loads. The connectors are not designed to handle that type of load. And so if you have a structure that's in torsion, we ask that you maybe give us a call, and we can figure out how to redesign your structure so that it's not subject to torsional loading. So today we're going to talk about axial loading and bending loading and how that affects what profile you're going to choose. So in axial loading, as I said, we're pushing down on this, and we're subjecting all of the material in this to compression. So what's important in how much load this can take is how much material we have in the cross-sectional area. The more material, the more load we're able to react. In bending, that's a different story. In bending, what we have is when we press down on this, the top of this is going to bend down like this, and it's actually going to get longer. The beam wants to get longer across the top. And so what we see is the material at the very top is actually going to be trying to pull apart. It's going to be in tension. The bottom of this is the opposite story. It's going to come in like this, and it's going to try and get shorter. And so the bottom of the beam is going to be in compression. What you have is tension at the top, and this transitions to nothing at the centroid, it's called, and then it's compression at the bottom. And this is the way that the structural member is able to react to load. It's basically you have this coupling between these two different stresses, and that's what provides the resistance to a bending load. Now it's important when we look at that is we know how that stress is distributed. You have the most stress at the top, at the very outermost part of the beam, either in tension or in compression. And so if we want a strong beam, what we want to do is we want to get most of the material at the very outer edges of the beam. And if you think about one of the most classic shapes for a beam is an I-beam, where you have two flanges, where you have all the material either at the top or the bottom connected by a thin web. And that's why it's designed that way, so you get that material as far away from the center of the beam as you can so that you can react the most load. So what we see that's different in a bending load from an axial load. In an axial load, we just cared about how much material that we have here. And in a bending load, it looks like the shape of the beam is going to affect how much load we're able to carry. And in fact, the shallower the beam depth is, the less it's going to be able to react because we have this coupling force. As opposed to if I had a deeper beam and I had that same stress, I'd be able to react a much greater bending load. We could demonstrate this actually with a simple piece of paper. We'll see how the shape of a beam affects its ability to carry a bending load. So here I just have an ordinary tablet paper, and let's just say that this is a beam. And I press down on it, and of course it's a very poor beam. It's very weak, as you can see. All I'm going to do, same piece of paper, all I'm going to do is I'm just going to change the shape of that. We're just going to bend this up a little bit. Now I'm going to press down on it, and you see it's a much stiffer beam. It's able to carry a much greater load. What happened? Well, in the first example, my beam depth was literally the thickness of the paper. And in the second example, when I bent this up like this, my beam depth was what you see here. And so we see that the shape of this, like I said, is really important in how much load a structural member is going to react. Now, how that relates to what type of profile you should select, depending upon your loading, is what we're going to talk about in Part 2.